In the previous lesson, we looked at how different simplifying assumptions transform the full Navier-Stokes equations into more tangible forms. We were able to reduce the momentum conservation equation to the famous Bernoulli's equation by assuming that the flow is incompressible, inviscid, irrotational, isothermal, steady state, and finally that the body forces that are being applied on the fluid particles are only due to gravity or can be neglected entirely. The class of flows that satisfy these conditions are generally referred to as the potential flows. Let us now mathematically define the potential flows. We know that these flows are irrotational. Based on vector calculus, whenever a fluid flow is considered irrotational, mathematically it means that the curl of velocity for such a flow is equal to 0. The velocity field for such flows can be expressed as the gradient of a scalar. This scalar function phi that is dependent on the velocity of the fluid is referred to as the velocity potential. If we now plug in this identity into the continuity equation, we arrive at the famous Laplace equation. Before the advent of complicated numerical algorithms that can directly solve the original Navier-Stokes equations, the Laplace equation was the one which was used to find the solution for simple fluid flows. Another feature of the Laplace equation is that it is a linear equation. As a result, multiple solutions of the Laplace equation can be stitched together to create a more complicated flow field. This technique is referred to as the superposition, which we will look at in our next lesson. In general, to solve the Laplace equation, we need to specify the domain over which the equation will be solved and the conditions at the domain boundaries that the solution needs to satisfy. These conditions are referred to as the boundary conditions. Mathematically, the Laplace equation is an elliptical equation. For such equations, there are two types of boundary conditions that can be specified. One, a Dirichlet condition, where we directly provide the value of the potential. Two is the Neumann condition, where we specify the derivative of the potential. You must be thinking, how do I know which boundary condition to specify? Well, let me explain that using an example. Let's say that our aim is to calculate the lift generated by an aircraft wing. For simplicity, let us consider a 2D flow. In 2D, the shape of a wing is represented by a profile referred to as an aerofoil. Since the first step is to define the domain over which we need to solve the equation, let us now enclose the aerofoil inside a domain and impose that the flow is coming in through the left face and leaving through the right face. The problem is now defined and we will now have to impose some boundary conditions. The airfoil is a solid object and will be designated as the wall. We will also designate the top and the bottom faces of the domain as walls. Physically, a wall boundary imposes that no flow can pass through it. Mathematically, this means that the normal component of velocity at the wall is 0. The left and the right faces of the domain are designated as the inlet and the outlet boundaries. Since we know that the flow is entering and exiting the domain through these boundaries, the velocity of the fluid at these boundaries is known and is equal to the gradient of the velocity potential, which we know. Till now, we have discussed the potential flows from the standpoint of the velocity potential. We will now introduce another function that comes in handy when deriving the analytical solutions of the potential flow equations. Let us now recall the continuity equation for the incompressible flows. We have that the divergence of velocity is equal to 0. Expanding this equation for two-dimensional flows, we get the following form of the same equation. If you notice, this equation requires the knowledge of two components of velocities in order for it to be solved. Let us now define a function called psi in the following way. Now, let us consider the equation for the differential form of psi. Notice that the circle terms are nothing but the velocity components that we just defined. Substituting for them, we get the following form of the equation. This equation should look very familiar. It is in fact the equation that defines the streamline in a 2D flow. Streamlines describe the direction of the motion of a fluid. Since the function we introduced defines a streamline, it is referred to as the stream function. It can also be proved that for the potential flows, stream function also satisfies the Laplace equation. I will let you do that. At first sight, it is very hard to see the distinction between the velocity potential and the stream function, but let us try to list them out. Velocity potential requires the flow to be irrotational. Stream function, on the other hand, does not. The velocity potential is valid for three-dimensional flows. Stream function is defined only for two-dimensional flows. Constant velocity potential lines are called equipotential lines, whereas on the other hand, constant stream function lines are called the streamlines. In fact, these two lines are perpendicular or orthogonal to each other. Now that we know what a stream function is, and we know that it also satisfies the Laplace equation, we can solve this equation for either the velocity potential or the stream function and extract the flow field velocity components. If we now refer back to the airfoil problem that we wanted to solve, and now consider that we want to find the stream function, we need to define the boundary conditions for this stream function. Let us first consider that the wall boundary condition, which we have defined as a boundary through which no flow penetrates. We have defined a streamline also as an object across which no flow can pass through. Based on these two definitions, it is now easy to see that a wall is nothing but a streamline. As for the inlet and the outlet, the boundary conditions for the stream function at these locations are analogous to those we have for the velocity potential. With that, let us wrap up this lesson.